Welcome, everyone. We are really excited from the Clivar Pacific Regional Panel to be hosting this series of webinars based on ENSO. And we're especially excited to have Jérôme Vialard from the French National Institute for Sustainable Development, who's been working in the ENSO theory space for a long time and has made advances in our understanding of ENSO to help us start us off and get us on the same page of the latest developments of ENSO theory, specifically the recharge oscillator. Jérôme, please take it away.
Okay, thank you very much. So let me put my screen in full mode. Okay. Well, thank you very much. First of all, it's an honor to start this series. I've been long associated with Clivar through the Pacific panel and formerly the Indian Ocean panel, and I'm really actually glad to give this opening talk on ENSO. So I may not be actually an ENSO theory specialist. Actually, my venture into this area has been quite recent, but I'll come to that point a bit later. Why I think I'm qualified to give this talk. So before I do that, let me introduce our two main characters of today's show. Actually, so these are El Niño and La Niña, and you see the little cartoon. The boy is saying, "Niños are stronger than niñas." The little girl is answering, maybe Niño, but niñas last longer. So we'll see that both these statements are true. And so El Niño is a bit hot-tempered, as you see, but fortunately, La Niña is cool. So of course, these two little cartoon characters stand for the two phases of our favorite climate oscillation. So as you can see during La Niña, so this picture shows SST anomalies in December 1988, and you see a cold anomaly over most of the equatorial Pacific Ocean. So that's a La Niña situation. And the opposite phase is like the one we had in December 1997, corresponds to warm anomalies over most of the equatorial Pacific Ocean. And this corresponds to an El Niño situation. So an usual way to look at the time series of ENSO is to take SST anomalies in this region in black, Niño 3.4 region that I've highlighted here. And this is the time series below. We can remark a lot of features actually already from this time series, but the first thing we can indeed verify is that the two little cartoon characters were correct. I mean, you see that El Niño events tend to be larger. They sometimes exceed 2 degrees in amplitude over in average over this area, whereas La Niñas tend to be a bit smaller, less than 2 degrees in general, but they tend to last a little bit longer. If we want to go a bit further in this ID card of El Niño, so the way we can define a climate phenomenon is through a couple of properties, so like the amplitude, some kind of dominant periodicity, maybe the seasonality. And so if we look at, we can see all of these features from this time series. So we see that if you work out the standard deviation of this time series, its amplitude is about 1 degree Celsius. You see that there is no clear dominant periodicity. Actually, if you take a look at the time interval between two peaks of the same sign, you can find it varies a lot between 1 and 8 years over the last 50 years or so. So there's really a broad spectral peak, not a single defined periodicity. Another thing which is a bit difficult to see on this time series is that all the peaks are neatly lined up with the seasonal cycles. They peak in boreal winter, El Niño peaks in boreal winter. And the last feature I already mentioned is that El Niño events tend to be a bit larger than La Niña events. So actually what I will show you today is that we now have a simple theory for ENSO, which can account for all of these properties, and actually even more than these properties. So we'll come to that. Okay, so this is a time series from the paper of Bjerknes 1975. So the black curve here is showing the climatology, the over spiky curve is showing actual temperature anomalies. And you see that in 1972, the ocean was unusually warm. I mean, it's marked by the red shading here. So there was a quite large El Nino in 1972, one of the 4 largest El Nino in the last 50 or 60 years, actually. And so why I feel I'm somewhat qualified to give this talk is that actually I was born in June 72. So I don't think that this is a large enough statistical sample to say that I can trigger El Nino events, but hopefully I can discuss El Nino events. So that's what I'm going to do today. And I'm going to do that. I'm going to use material from a lot of people to do so. So the first important source of material you probably all know is AGU ENSO monograph that was edited by Mike McFadden, Agus Santoso, and Wenju Chai. It's a wonderful resource on ENSO. Another nice resource, I was a lecturer in ENSO Winter School that was organized by Christina Karen-Peridou in Hawaii last March. And also I will use a lot of pictures actually from this open access, so you can go to the web and download it, reviews of geophysics, review of the Recharge Oscillator. And I will also draw material from one chapter on ENSO in an encyclopedia of climate system sciences that is currently underway. Okay, so let us get started. So I'll start by briefly remind you why we study ENSO, why ENSO is important. I will then continue by a very brief history of ENSO science, trying to underline important ideas along the way. Then I will summarize how we can put essential ingredients together to build a simple recharge oscillator. And then we'll see that we can add a couple of things to this simple recipe to get a full recipe for the El Nino phenomenon, which can account to a lot of the properties I've been discussing before. And then I will end by what are the aspects of ENSO research that the Recharge Oscillator doesn't fully yet address, and what do we need to do in future. So let's start with why study ENSO. So this picture on the left is showing the leading EOF of the detrended sea surface temperature anomalies over the last 50 or 60 years. And you see that this leading EOF is clearly El Nino, an El Nino with a warm anomaly in the Pacific. And if you work out the percentage of variance explained by the first 5 EOF, you see that this leading EOF, so ENSO, explains 3 to 4 times more variance than the next EOF. So ENSO is really the dominant pattern of SST year-to-year variations globally. And you see that El Nino is not only associated with anomalies over the Pacific. I should activate the pointer, actually. Okay, so El Nino is not only associated with SST anomalies over the tropical Pacific, but also to SST anomalies in a lot of other regions. And you see that there are warming in equatorial Indian Ocean, in some regions of the Atlantic during an El Nino. So in fact, El Nino is associated with a global warming signal. And this you can see very clearly on a time series of the global surface air temperature, where La Niñas are represented as blue stripes and El Niños as red stripes. And if you look at this time series, the first thing you see, of course, is the long-term trend associated with global warming. But superposed to this, you see variations, and you tend to see a cooling during La Niñas and a warming during El Niños. And this is the global warming signal that peaks the year after ENSO, and which is associated with 0.1 to 0.3 degrees Celsius anomalies in terms of global surface air temperature. And there were a couple of papers, actually, in particular Kosaka and Chi in 2013, which demonstrated that because of this imprint on global temperature, El Niños, the decadal modulation of El Niño contributes a lot to the modulation of the global warming signal, where and that you have basically a slowdown of global warming during negative phases of the Pacific decadal oscillation during decades where you have a lot of La Nina. Okay, that's a first good reason to study ENSO. A second good reason to study ENSO is that it has impacts almost globally. So these pictures are from the paper by Andrea Tacheto in the AGU monograph, and basically there are two different mechanisms for tropical teleconnections and extratropical teleconnections. So during an El Nino event, because you have large anomalies, large SST and rainfall anomalies, there are very strong zonal shifts in the Walker circulation, so the overturning vertical circulation in the equatorial plane. And because of this, you create anomalous subsidence or ascendance on over remote regions, and therefore atmospheric anomalies over remote regions. The second pathway to extratropical teleconnections is that the heat source of thing associated with El Nino or La Nina events can generate standing Rossby waves, which are guided by the mean atmospheric barotropic flow into the extratropics. And this creates these patterns of alternating positive and negative sea level anomalies that extend into the northern and southern hemisphere. So basically, these are two ways by which El Nino can modify atmospheric conditions remotely and can also induce remote imprints on remote sea surface temperature. Because of this global impact on climate and weather, there are, of course, many impacts that many aspects of ENSO that impact human life. So ENSO has a strong impact on marine ecosystems and fisheries, on droughts. During an El Nino, there tends to be a drought in Australia, and there tends to be floods in South America, amongst other places. El Nino is also a primary cause for large-scale marine heat waves. And because El Nino influence rains and rain influence vectors of disease like malaria, El Nino has an impact on health, actually. It has an impact on food safety. For example, for its impact on agriculture, it can impact food safety. Wildfires, tropical cyclones, there is a long list. I mean, some way to quantify this is that the cost of an extreme El Nino event has recently been evaluated to in a range of $4 to $6 billion. So it measures how really huge the impact of ENSO on the global economy is. Okay, but now, so ENSO has a lot of global impacts. Can we foresee these impacts in advance? Actually, we can. We know this since the early forecast performed by Kane and Zibiak in 1986. And the picture to the right is giving more an idea of the state of the art. So it shows the correlation skill as a function of lead time of ENSO forecasts. And we see several systems here. So conventional statistical models, dynamical, so coupled ocean atmosphere general circulation models, artificial intelligence. And you see that typically you achieve a .6 skill, which is usable skill, 7 to 11 months ahead of the El Nino peak, which means that El Nino has global impacts and can be forecasted about 6 months to a year in advance. And because of that, it's a key provider of predictability, seasonal predictability of the climate globally. So it's therefore super important to be able to understand and forecast El Nino. And maybe the last aspect I would like to underline is that El Nino is also some kind of paradigm of climate variability. So we can think of two big paradigms of climate variability. The first one is relevant for mid-latitudes. So this is stochastic climate models theory of Hasselmann in 1976, which can explain climate variability associated with, for example, the Pacific decadal oscillation in North Pacific or Atlantic meridional overturning oscillation, multidecadal oscillation in North Atlantic. And the idea there is that the ocean is acting as a memory to these oscillations by integrating random variations of large-scale atmospheric patterns, such as the PNA and NAO. So here, the ocean is kind of passive by passively integrating atmospheric stochastic variability. In the tropics, so Jean in 1997 provided the theory for the Recharge Oscillator, which is, as I will try to show you, one of the most advanced theory of ENSO that we have today. There, it's slightly different. The ocean is also playing a strong role as a memory of the climate system, but we have a more active role of the ocean. It's because of ocean-atmosphere coupling that El Niño events can grow, and we'll see this in more detail. Okay, for all of these reasons, I think you will agree with me. It's really important to study ENSO and to forecast it. So we'll start now with a super brief and subjective, of course, history of ENSO science, the important ideas. Then we'll see how important ingredients can be combined into a simple recharge oscillator that can explain the oscillatory behavior of ENSO. And then we'll add a bit more ingredients to cook really a full ENSO before we end on future of ENSO research. So let's start with this brief history of ENSO science. And where this history starts is actually in South America. El Niño has a lot of impacts in South America, and more on the side of the ocean. The first documents that talk about El Niño in scientific literature were in Bulletin of the Geographical Society of Lima in Peru, in South America. And Luis Carranza in 1891 was the first one to mention a warm ocean countercurrent, which was synchronous to flooding in Peru. Later, Camilo Carrillo in 1893 mentioned that fishermen were calling this phenomenon El Corriente de Niño, because it was happening near Christmas, so and El Niño being in the word for child and infant Jesus in Spanish. And Eguiguren in 1894 made one of the first chronology showing that these warm anomalies, these warm oceanic conditions, were often associated with flooding in Peru. Okay, quite independently, and about 30 years later, Sir Gilbert Walker was stationed in India, in the Indian Meteorological Department, and was looking at correlations between pressure in various atmospheric pressure in various meteorological stations globally. And the way we can summarize finding with a more modern figure here is by looking at the correlation between this index, which shows the pressure difference between Tahiti and Darwin, and which features kind of low frequency oscillations, which each event lasting about a year, and sea level pressure everywhere. And you see that Walker basically underlined what he called the Southern Oscillation, which was a global scale, low frequency atmospheric pressure seesaw, so shift in the atmospheric mass between a large area around Australia and the Southern Pacific, which he called the Southern Oscillation. And it's again about 30 to 40 years later that Jakob Bjerknes, in a couple of papers, found that the Southern Oscillation and El Niño were actually two sides of the same puzzle. So if we bring the Southern Oscillation, so the atmospheric time series, and the Niño 3.4, so the oceanic time series together, you see that there is clearly an anti-correlation between the two time series, with peaks, El Niño peaks, being associated with negative values of the Southern Oscillation. So Bjerknes was the first one to introduce the idea of coupled ocean atmosphere feedbacks, giving rise to El Niño, La Niña development. The The next main achievement was brought in 1975 by Klaus Bjerknes. This is a very nice paper. I really encourage you to read this paper. It's amazing what Bjerknes could achieve with quite little data. He could add a lot of intuitions, which are shown by this more modern figure relying on much more data. So this figure is showing the lead correlation between oceanic heat content in the Pacific, and in particular, the red curve is showing the Western Pacific heat content, and El Niño. And you see that there tends to be a peak correlation about 1 year in advance, implying that basically high Western Pacific heat content sets favorable conditions for El Niño. So preconditioning by the ocean. Then people try to think about what was the mechanism for phase transitions, and the first theory for this was the delayed oscillator theory. Basically, let's take a look at this picture on the right. The idea of the theory is that basically, so this is a longitude time diagram showing that during an El Niño, you have westerly wind anomalies, and these wind anomalies force fast waves, Kelvin waves, which are going to help the El Niño to grow, the downwelling Kelvin wave. But at the same time, it's going to force slower Rossby waves, propagate to the western boundary, come back at upwelling Kelvin waves, which on the other hand are going to make the El Niño decay. And basically, they summarize this by an equation which has both a growth term, so the Bjerknes feedback, but also a delayed decay term, which is supposed to represent the way in which ENSO wind anomalies sets up the conditions for its own demise a couple of months later. And so this was the main ideas of how El Niño can eventually terminate and shift into La Niña. At the same time, there were efforts in developing simple models. So the Kane and Zibiak was the first simple model of ocean atmosphere coupling in the tropical Pacific. This model both allowed the first experimental forecast, El Niño forecast, showed it was possible to forecast El Niño, and also he kind of demonstrated that a simple model could qualitatively reproduce several ENSO features. And in particular, this model, they demonstrated that the ideas of Bjerknes of the role of the important of the heat content was also playing an important role for phase transition. So another idea to back up the role of the ocean in ENSO phase transitions. And it was later, so in the late 90s, that Fefejin did come up with a theory which he named the Recharge Oscillator theory, which basically could explain both the El Niño preconditioning. So the idea is that when you have an anomalously high heat content in the Pacific, it sets favorable conditions for an El Niño development, but this El Niño is inducing actually sphere drop transport, which is going to remove heat from a tropical band, result in a discharged tropical band, which itself will set favorable conditions for a shift to La Niña. So here, the novelty is that you have a single theory that explains that represents both the role of heat content, but also represents both preconditioning, so how oceanic content set favorable conditions for El Niño, and how El Niño influence oceanic heat content. Okay, but of course, we can, all of what I'm going to present today based on the Recharge Oscillator was obtained by many sources of studies. One of them, of course, is the observations of the tropical Pacific. And one important step in this was the Toga decade. So Toga was an ancestor of Cliver, actually, the WCRP program. And one of the big achievements of Toga was to develop a full observing system of the tropical Pacific, relying on many things, so of voluntary observing ships, tide gauges, drifting buoys, and also what became later the Tau Triton array. And this has allowed a lot of understanding of El Niño. Another big achievement of the Toga decade was also moving from the simple models like Kane and Zibiak into coupled general circulation models. And there's a good summary of this by my former PhD advisor, Pascal Delecluse. Okay, to end this tour of important discoveries about El Niño, I need to mention westerly wind bursts. And westerly wind bursts were discovered as fast wind variations. So let me maybe first describe the picture on the right. So this picture here is showing a longitude time evolution of winds in colors and SST in contours during the 97-98 El Niño event. And what people remarked early is that in addition to the low frequency, more or less 1 year long gill wind response to warm SST anomalies involved in El Niño, there were also fast wind variations, which people name wind bursts, which played an important role in triggering oceanic Kelvin waves that allow this El Niño to grow. And another thing that people remark quite early is that as an El Niño warm anomaly develops, these westerly wind bursts can migrate into the Central Pacific and become more active. And we'll see that, so both the fact that there is this random fast atmospheric forcing that can trigger an El Niño, and the fact that this atmospheric forcing is not completely random, but also made more efficient by El Niño, will play an important role. Okay, so now let me describe in details, in a bit more detail, the two essential ingredients that allow that are at the heart of the ENSO theory. So the first one is the Bjerknes feedback, and a good way to introduce the Bjerknes feedback is to come back to a description of the mean state of the tropical Pacific. And so you see in the tropical Pacific there is a temperature gradient between the warm pool, so in Western Pacific, and colder water of the cold tongue. And actually, this gradient is contributing to maintain trade winds, so easterlies, that blow towards the Western Pacific and which are the lower part of the Walker cell. But at the same time, these trade winds exert a westward force on the ocean that needs to be balanced by an opposite pressure force. So you need to lift the sea level and deepen the thermocline in the Western Pacific. And on the other hand, you need to lift the thermocline in the Eastern Pacific. Another consequence of the trade winds is that they maintain upwelling, and because the thermocline is closer to the surface in the Eastern Pacific, this upwelling is going to result in a cold tongue here. So you see that in my description, I've told you the east-west gradient is contributing to maintain the trade winds, but the trade winds themselves maintain the east-west gradient in temperature. So it introduced the idea of Bjerknes that there is a feedback loop between the ocean and the atmosphere. So let us move now to El Niño anomalies. So these are typical El Niño anomalies obtained by regression to an El Niño index. The first panel here is showing SST in colors, rainfall in contours, and winds in green arrows. And you see that during an El Niño, you have more rainfall in the Western and Central Pacific. And through the theory of Gill, this induces westerly wind anomalies over the Pacific. So this picture here is showing basically how this westerly wind anomalies, this is a blue curve, is creating a slope in the sea level gradient. And basically there is a balance of force between, so this is the equatorial standard balance between the force of winds on the ocean and the opposite pressure gradient. And because of this, you lift the thermocline in the Eastern Pacific, so this generates warm subsurface anomalies, and whereas you deepen it in the Western Pacific with cold subsurface anomalies. Because there is an upwelling in the Central and Eastern Pacific, these warm anomalies are going to reach the surface and warm the surface. So you see that here I've described how a warm anomaly through its impact on winds and the ocean atmospheric, will cause upwelling of warm water and therefore more warming. So this is basically what we call a thermocline feedback, which is one of the most important ingredients of the Bjerknes feedback. Okay, if we want to put this in equation, so we can write a simple heat budget of the Eastern Pacific, just retaining the effect of the upwelling. And basically, so I'm not asking you to look at the detail of this equation, but you see that there is a W bar, which represents the intensity of the upwelling, and the surface will warm if there is an anomalously warm subsurface temperature anomaly. So if you have warm anomaly here, the upwelling will warm surface. This is what is expressed by this equation. And now we would like to transform this term so that it is proportional to TE and can describe basically exponential growth or decay of the TE anomalies. So to do that, we can, and this is from Jean et al. Papers in the AGU monograph in 2020, try to see what is the relation between subsurface temperature anomalies and thermocline anomalies. And you see that it's a linear relation. Then we can see that the Eastern Pacific thermocline anomalies themselves are proportional to change in zonal wind. So this is the sphere drop balance, and this is again a relatively linear relation. And finally, we can also look at how the wind anomalies are depending on SST anomalies. And this is also to first order a linear relation. And this is the Gill response of wind stress to SST anomalies. If we put these three terms together, then we can express the rate of change of temperature anomalies in the Eastern Pacific as proportional to the Eastern Pacific temperature, with the thermocline feedback component of the Bjerknes feedback, which can be written like this, implying the multiplication of these three terms and also an efficiency which depends on the upwelling. So if this is positive, this will favor exponential growth of anomalies, initial anomalies, both positive and negative. So this is an unstable part of the Bjerknes feedback loop. But actually, there are more processes in the Bjerknes feedback in addition to this. So I've just described here the feedback loop between SST, rainfall, wind stress, thermocline, and SST, which is the thermocline feedback loop. So this is this loop that I'm following here. But of course, there are other components, other mechanisms in this loop. Another important mechanism is that if you warm the ocean, it's going to lose more heat to the atmosphere. And the clouds, the associated clouds, will also reduce solar flux, so which means the ocean is going to gain less heat. So it's a cooling term, an anomalous cooling term, which will limit the growth of the El Niño. So RC fluxes are associated with negative feedback. And there are also other processes like current anomalies can also help pushing the thermocline into the Central Pacific. This is also positive feedback. So there are various, I'm not going to go into the details, but the Bjerknes feedback is the sum of various various feedback components, some of them positive, some of them negative. So what Fefe-Jean did is, if you do this computation for more terms in the upper ocean heat budget equation, you can come for a full expression of the Bjerknes feedback. It's quite a complicated equation that expresses whether the Bjerknes feedback is positive or negative as function of the ocean mean state and other coefficients like the intensity of the coupling between winds and SST. And you can work out the amplitude of various contributors to this Bjerknes feedback. So you see that on average, the Bjerknes feedback is positive. It allows anomalies to grow. But actually, it's a balance between positive and negative terms. And the main two terms, if you want to remember them, is the thermocline feedback. So the first one I described is the main term for growth. And the thermodynamical feedback associated with RC fluxes is the main term for decay. So we'll keep mainly those terms in mind for the following. Okay, so now we all know that the tropical Pacific has strong seasonality. How will it impact the Bjerknes feedback? So I write again the equation here for the two dominant terms. So this is the thermocline feedback and the effect of RC flux, which is negative and quite constant all year. And you see that the thermocline feedback is proportional to the upwelling intensity. And this is the typical seasonal cycle of wind stress in the Eastern Pacific, with stronger easterlies going downward. And you see that easterlies and the upwelling tend to be strongest during boreal summer, so during July to December period. And this is also the period where you can diagnose the Bjerknes feedback, which is largest and positive. So this will play an important role to explain the phase locking of ENSO. Okay, another ingredient that we need if we want to account for the preconditioning effect of the heat content is an explicit equation for the equatorial heat content. The trouble is that equatorial dynamics are quite complex. They involve Kelvin, Rossby wave, various baroclinic modes, reflections at both boundaries. But actually, there were a couple of seminal papers that showed that you can average these complex dynamics along the equatorial band into a relatively simple equation, which I show below. And this simple equation just has two terms. So one of these terms, which here is written for the Western Pacific heat content. So the first term is simply saying that if in absence of forcing, if you have a Western Pacific heat content anomaly, eventually it will decay because you lose information toward higher latitudes through surge transport. But there is a second term in this equation that represents wind forcing. So basically, during El Niño, you have westerlies, and you expect to have a decrease of the heat content in the Western Pacific, negative subsurface anomalies. This is what this term is representing. If T is positive, you will make HW decay. This equation is really super simple, but as you see, you can compare the observed evolution and that predicted by the equation, and you see that there is a really good agreement between the two. So this equation represents, to first order, the variations of the Western Pacific heat content. So now we can piece back the two equations that we have. And this is what Fefe-Jean did in the Recharge Oscillator. So we can have a first equation for the Eastern Pacific SST, and a second equation for the Western Pacific heat content. So I've just explained this equation. The first equation has two terms. The first one is the Bjerknes feedback. So when it is positive, it will create exponential growth of temperature anomalies. But we need also to account the second effect, which corresponds to the delayed feedback from oceanic dynamics, which correspond to the fact that when you deepen the Western Pacific thermocline, you will also deepen the Eastern Pacific thermocline, and this will have an effect of temperature. Okay. So this is the equation for an oscillator. You can work out what we now call the Bjerknes-Vialard index, which is a complex number, and the real part of this complex number is giving the growth rate of anomalies here, which can be written r minus epsilon divided by 2. It involves both r and epsilon, and also which can predict the frequency, which is this part. Okay, so this is an oscillator, and now we can try to see what is the growth rate of this oscillator. Oh, no, sorry. Before we do that, I would like to explain in simple words how this oscillator works. So let us imagine that we start from a recharge state. So we have HW positive. Because HW is positive, this will favor warming in the Eastern Pacific. So this positive term will favor warming of Eastern Pacific SST. Once you start to have a warm anomaly, it will grow through the Bjerknes feedback. So this recharged system will tend to evolve to a fully grown El Niño. But during a fully grown El Niño, you have positive temperature anomalies. So this term is negative, and this corresponds to the effect of the sphere drop transport outside of the equatorial band, which will make the Western Pacific heat content, in general, the equatorial band heat content, decrease, and will eventually result into a discharge state of the ocean, which will then favor a transition to La Niña. So the Recharge Oscillator is showing this full cycle. Okay, so now that we have all of these elements, let's start cooking a good El Niño. So to cook a good El Niño, so I just told you the essential elements are the basic Recharge Oscillator, and we are slowly going to add the other elements in this equation, which will allow to explain most of the El Niño aspects. So it's because of the Bjerknes feedback. So in a good recipe, you need to turn up the heat to start things growing. So this is what the Bjerknes feedback is doing. These terms of the equation, as I just told you, represent the oceanic delayed negative feedback. So it allows to flip over if you cook some pancake, actually, and to change the phase. But actually, what we are going to show soon is that we need to keep steering through stochastic atmospheric forcing to maintain the system in a moving state. We need to have a well-timed Bjerknes feedback to only serve in winter, to have El Niño peaks in winter, and with non-linearities to have stronger El Niños than La Niñas. Okay, if you try to compute the value of R minus epsilon divided by 2, either from the theory, the big equation I showed you a bit earlier, or from trying to fit the Recharge Oscillator equation to observed time series, or to models, actually, you obtain negative values. So you obtain a system which is asymptotically stable for both observations and all semi-models. So basically, if you don't do anything to the system, oscillations won't be maintained, they will die. So you need to keep steering, you need to add stochastic forcing to maintain the oscillation. And there is all debate actually about whether El Niño should be viewed as a self-sustained nonlinear oscillation, so something which sustains itself without the need of external stochastic forcing, or whether it's driven by noise. Actually, I won't get into the detail, but there are several papers that show that both in the Kane-Zibiak model and in a Recharge Oscillator, the noise-driven stable system hypothesis yields more realistic statistics of ENSO. So I would say this whole debate is leaning more toward B presently. Okay, and indeed, so these are two pictures. So this table, noise-driven Recharge Oscillator, can reproduce both El Niño amplitude and spectrum. So let me describe these figures. So this figure here is showing so the amplitude of ENSO as a function of stability. So this R minus epsilon divided by 2, and the amplitude of the steering, the amplitude of the stochastic forcing we're adding to the system. As you intuitively can feel, there is a growing El Niño amplitude when you add more steering and the system becomes less stable. And all of these circles here represent various couple models from CENIP, and the star is showing observations. And if you do a scatter plot between the actual CENIP 6 or observed ENSO amplitude and that predicted by the Recharge Oscillator, you see a very, very good behavior. So the Recharge Oscillator can predict El Niño amplitude in both observation and CENIP 6 models. The right figure is showing the Niño 3.4 spectrum, so the black curve is observations, and the two blue and red curves are two versions of the Recharge Oscillator. And you can see that also the Recharge Oscillator, when it's driven by noise, can also reproduce very well the really broad spectral peak of ENSO between 2 and 7 years in observations. So first two successes of the Recharge Oscillator, you can reproduce both El Niño amplitude and spectrum in actually observations and models. I'm not showing it for models here, but that's also the case. Okay, so you add the stochastic forcing as two terms in the equation. So the xi terms here are, zeta terms here are stochastic random variables, white noise, and the sigma are showing the amplitude. Because you add some random terms here, you're going to make the cycle irregular. Let me give an example. If you start from a neutral state, and if you have a positive sigma here, this will generate a positive anomaly, which can grow into an El Niño. Similarly, the random forcing can store information in the age variable, which can set up favorable conditions for an El Niño growth. So the effect of adding this stochastic forcing, the first effect is to make the cycle irregular. You won't have a regular cycle that follows, recharge, El Niño, discharge, La Niña, but you can move toward between various parts of the cycle. The second effect is because you have some random effects here, this is no longer a deterministic equation, and this is going to limit the predictability of your system. Okay, now if we know that El Niño is peaking in boreal winter, so this picture here is showing the observed El Niño variance. These are the gray bars as a function of the time of the year, and you see a clear peak in November, December, so in boreal winter. Actually, you can reproduce very easily this peak with the Recharge Oscillator, so this is the red curve, by simply imposing seasonal variations of the Bjerknes feedback. You don't need actually seasonality in the other terms, and just by using sine Bjerknes feedback with a peak in summer, basically, you're going to have the most growth of anomalies during summer and fall, which will favor a peak in winter. And so by adding this seasonally dependent Bjerknes feedback, you can reproduce the El Niño seasonal synchronization. The last aspect, I told you that El Niño events are bigger than La Niña events. If you want to reproduce this, you need to add some nonlinearities in these equations. And so these are these two terms here. And you see that the first effect of this nonlinearities is deterministic. It's simply proportional to t squared, which will have the effect of increasing the Bjerknes feedback, but only for positive. So for positive El Niño, it will increase the Bjerknes feedback. For negative anomalies, it will decrease the Bjerknes feedback. So it will make the growth of El Niño more efficient than the growth of La Niña. And so this can represent various physical processes, but recent studies really emphasize the role of the relation between atmospheric convection and SST for this process. And the second term is stochastic. It's to represent the fact that wind bursts, westerly wind bursts, are stronger during El Niño. And basically, so you see that you have your stochastic forcing term, and this term here is going to make the forcing by stochastic burst larger during El Niño than during La Niña events. And by adding these two terms, you can, so this is a time series from observation with a skewness, so which shows a shift of the time series toward El Niño of 0.35. And you see that the Recharge Oscillator with these two terms in can reproduce qualitatively the asymmetries between the amplitude asymmetry between El Niño and La Niña with a very similar skewness to observations. Okay, so the Recharge Oscillator is a successful ENSO recipe. It can reproduce ENSO amplitude and spectrum by representing El Niño as a noise-driven stable oscillator. It can represent seasonality as well, and it can represent the fact that El Niño events are stronger than La Niña events. So I've been speaking quite long already, so I should be a bit fast for the end. So I'm going to try to tell you now what the Recharge Oscillator does not represent well and how we can make it evolve in future. So I've not been discussing a quite important part of El Niño research over the last 20 years, which is ENSO diversity. There is a nice review of this by Antonietta Caputandi in 2020. So this plot basically is showing that SST anomalies at the peak of the large El Niño and La Niña events of the last 40 years. And you can see that if you look at moderate El Niños in pink and La Niñas, they are quite symmetric, opposite and symmetric. But you see that as El Niño grow in amplitude, they become different in pattern with larger anomalies toward the east. And actually, because of this, you have different rainfall anomalies, different teleconnections, so it's quite important to be able to explain that. Another way to view this is that if you represent El Niños in a state of the two first pieces, the two leading EOFs of SST anomalies, so the leading EOF is of equatorial SST anomalies correspond to a homogeneous pattern in the Central and Eastern Pacific, and the second one is a dipole. And basically, you see that as PC1 increases, so as El Niños increase in amplitude, PC2 becomes more positive, so you have a larger contribution in the Eastern Pacific, and you make El Niño become a shift eastward. Whereas La Niñas also involve an increase of PC2, and stronger La Niñas also involve a westward shift. This is what this panel is showing here. I'm not so representing this in a Recharge Oscillator is work in progress. There have been studies that show that you can start to qualitatively represent this, and you can do this in two ways. The first way to do this is to have a T variable of the Recharge Oscillator that represents the worm pool edge instead of representing SST in a specific location, because as you can see here, the colors of this symbol is showing the worm pool edge, and you see the worm pool edge as you move toward purple toward red, you can map the evolution of this curve. So actually, you can relate nonlinearly this variable to the full SST field. And another possibility is to add one extra variable in a Recharge Oscillator to be able to represent both SST variations in the east and in the west. So the bottom line is that in both cases, you need to add nonlinearities in a system. And the bottom line is that people have been doing progress, but more research is needed. A second big area of El Niño research over the last 40 years is that El Niño is an interactive system with other basins. When you have SST anomalies, so this is from a review paper by Wenju Chai, and there have been many studies that show that SST anomalies in remote region can induce wind signals over the Pacific, which can make then influence the evolution of El Niño. So these SST signals can either be caused by El Niño in the first place or be independent from El Niño, and many regions have an influence. There is a nice review by Wenju Chai on this. There has been a huge progress done by this on this recently. So there is a very nice Nature paper by Senzao et al. In 2024, where basically they expand the Recharge Oscillator, which only accounts for the tropical Pacific, by adding variables that represent El Niño variations in other basins. And basically, this system of equation here is representing, so the yellow part is representing the intrinsic ENSO dynamics, but actually, this matrix here is going to influence both of how El Niño represent influence over regions and how other regions influence El Niño. I'm not going to describe this figure in detail, but basically what they show is that adding the interactivity with other regions strongly improves the forecast skill of the Recharge Oscillator. So the Recharge Oscillator forecast skill, when you account only for the Pacific, is in pink. And you see that adding the interactive interactions with our region strongly enhances the forecast skill to what you get in the X arrow in red, which beats actually artificial intelligence or other dynamical models. So we start to have a really nice theory for interactions between El Niño and other regions. And the last aspect I would like to underline is very important research, so El Niño in a warming world. So I'm going to summarize first very quickly what do we know about how ENSO has and will evolve in a warming world in climate models. So there are two review papers by Wenju Chai in 2021 and 2023, which show that El Niños seems to have already increased in amplitude and will continue to increase in amplitude in the near future. But the IPCC, the last IPCC report, underlines very strong uncertainties in this, so it's not completely sure. And also they underline that you really need ensembles to study El Niño. Basically, El Niño has a strong internal variability. Even without external forcing, you can have decades of strong activity of El Niño followed by decades of weak activity. So you really need to have a lot of ensemble members to be able to tell apart the external forcing signal from internal variability of El Niño. There have been also studies, recent studies, for example, that of Callahan in 2023, which show that if you increase a lot the CO2 level beyond what you will have in the mid of the 21st or in the 22nd century, you have a weaker ENSO. And indeed, recent studies which use large ensemble to look at El Niño show that the evolution of El Niño can be non-monotonic. So El Niño can first increase and then reach a plateau or decrease. So I would like to illustrate this with what you can do with the Recharge Oscillator. So the black curve here is showing the ensemble mean evolution of El Niño amplitude in one particular coupled model. And you see that in this coupled model, you have an increase of El Niño activity since the 1950s until 2020, and then more or less a plateau. In this model, some other models may go down, various models have different evolutions. And the red curve is what you obtain if you fit the Recharge Oscillator to the model ensemble. So you see that the Recharge Oscillator, by allowing coefficients of the Recharge Oscillator to change in time, you can represent changes in the El Niño amplitude. And then you can diagnose, so this is what the panel in the right is showing, what are the contributions of the change in various coefficients, in various parameters of the Recharge Oscillator explain this change. And for instance, you see that in this particular model, the initial increase is associated with a Bjerknes feedback which increases, which becomes less stable actually over time. And then you have other parameters. Okay, so but do we have a good theory of how the Bjerknes feedback change with climate change? And this is going to be my last two slides. Well, not really, and the reason why it is complicated. So let me come back to the two dominant terms here in the Bjerknes feedback. So this is the thermocline feedback here, and this is here the effect associated with damping by air-sea fluxes. So I won't go into the detail here, but I just want to emphasize that these parameters that I've highlighted, so this W bar parameter is the intensity of the upwelling. So this is a mean state parameter. And these other parameters, they describe other parameters like the coupling between wind SST or the coupling between the thermocline and the subsurface, which also depend on the mean state. So how this evolve, we don't have actually, and we don't know how these parameters are going to evolve. So we don't have a full theory currently of how this will change. But let us try to make educated guess. Under global warming, you warm the surface, so you increase, so you warm the surface. Because you warm the surface, because of Clausius-Clapeyron, you expect more evaporative cooling. So you expect alpha to grow, which will make the Bjerknes feedback more negative. So it will stabilize the system. On the other hand, if you have a stronger vertical stratification, vertical movements of the thermocline are going to create larger subsurface temperature anomalies. So you also expect A to increase, which will destabilize the system. So it's not obvious. There is actually two opposite parameters here which act, and it's not completely obvious which one will win and how the Bjerknes feedback will evolve. That's one. So stratification change is one effect of climate change, but also another effect of climate change is how will climate change influence the zonal gradient of SST and the mid-trade winds. And actually, as you may be aware of, there is this is a strong topic. There is a review paper by Watanabe et al. In Nature in 2024, which says that we don't even know how trade winds and zonal gradient are going to evolve in the future. Observations indicate a strengthening over the last 40 years, whereas models indicate a weakening over the last 40 years. So we don't even know how this will also influence the Bjerknes feedback, but we don't even know how this will evolve. So this is almost my last slide. So what do we need? So we need to use the Recharge Oscillator to diagnose ENSO changes in semi-ensembles and try to understand then how we can relate change in these various parameters to important parameters of the mean state change, like the uniform surface warming, we change vertical stratification, and change in zonal gradient and trade winds. And we also need a theory which allows to compute basically these Bjerknes feedback rho from the mean state directly without parameters that themselves depend on the mean state. Okay, so these are my closing words. So I told you about the key ingredients for a good ENSO recipe. So one is Bjerknes feedback that varies seasonally. The second super important ingredient is that ocean dynamics need to provide a delayed negative feedback, which eventually end El Niño and allow transition to the opposite phase. To make the system, to maintain variability in the system and to make it irregular, we need to have a stochastic forcing. And we also need to have weak nonlinearities, both in a stochastic forcing term and in a deterministic term, to produce a stronger El Niño than La Niña. So the recharge oscillator can reproduce many aspects of El Niño, like the amplitude, the spectrum, the El Niño seasonality, and the amplitude asymmetry between El Niño and La Niña. And the way forward, so I talked about diversity. We have already made good progress, and I think we are really underway to have a full theory for ENSO diversity. We still need consensus, but we are underway to have a full theory for ENSO diversity using the Recharge Oscillator. We also had a major step forward in describing Bayesian interactions using the X extended Recharge Oscillator. The area where I would say we need the most research is climate change. I showed you that you can use the Recharge Oscillator to understand how, for example, the Bjerknes feedback change in couple models, but we still need tools to understand how these changes can be related to changes in mean state. And with that, apologies for being a bit long, and thank you very much.
Thank you so much, Jérôme. No apologies needed. I think that was so interesting and a wonderful overview of how far we've come and what there is still left to do. I know we're at time, but if you are able to stay on just a little bit longer, then we can take some questions. If people have questions, they could put them in the chat. I would say they could raise their hand, but I actually don't know if on this platform that's possible. So either speak up or put this in, put your question in the chat.
Okay, so I'm trying to find where I can see comments or chat.
I will keep an eye on it.
The only question we have in the chat so far is whether this is recorded, and I think Agus mentioned this is recorded and this will be on YouTube. So I'm on my way to become an ENSO beauty influencer.
You're going to be even more famous.
Yeah.
Yeah, I maybe while we're waiting to see if people if people have questions, I had a question. So I really appreciated that explanation about the recharge oscillator and the different parts. And like you said, we still need theory that links the mean state without fitting the parameters.
Yeah.
And are there any thoughts that you have on that? I'm just, it seems such a hard problem.
So I agree, it's a hard problem. So in the review paper that we put together on the Recharge Oscillator, we give a couple of way forward. So one way forward is maybe we have a lot of coupled climate models which explicitly represent how, for example, important parameters for ENSO, like the coupling between wind and SST, depend on the background state. So we could use that and maybe statistical techniques or AI to try to describe nonlinear relations between these parameters and the background state. That's a possible way forward. I have reviewed recently a very nice paper from colleagues, so it's not out yet, so I cannot reveal the name of his colleagues. It is possible, actually, and in the initial paper of F.A. Jean, he actually started a theory for the Pacific mean state. So it's possible to modify the theory instead of trying to predict anomalies, you can actually formulate it in terms of mean state. The paper I reviewed has a clever way of adding external forcing on this. So I think it's a difficult problem, but I think there is a potential to make way forward and to eventually have a model that both represents the mean state and its response to anthropogenic forcing and El Niño. That probably will take 10 more years, but I think this is one of the way forward we should follow.
Thank you. Yeah, that sounds fascinating. Can't wait to read that. I don't see any more questions in the chat. I'm wondering if anyone from Cliver can see whether people can raise their hands and are raising their hands, because I can't see that.
Nobody raised their hands at this stage.
Thank you, Agus.
A very nice talk, Jérôme.
Thank you very much. Yeah.
Forward to many more webinars.
Yeah, we will, maybe before everyone has to run, we will continue the series. So keep your eyes peeled for another announcement on the next, probably in about 2 months, maybe a little more than 2 months' time. Agus?
No, just testing the button so everyone knows there is a button.
Thank you. So then I have, Jérôme, if you don't mind, I have another question.
No trouble, no trouble.
So something that I've been thinking about recently a lot is, and I know people are thinking about, is vertical mixing in the equatorial Pacific. So because you have the strong current shear, right, between the south equatorial current and the equatorial undercurrent, leading to mixing. And so I guess maybe from a smaller scale perspective, it's tempting to say that we need a more explicit representation of that process rather than sort of calling it the thermocline feedback. I'm just wondering.
Okay, so I mean, that's really a fair point. I think there are I think one of your question is related to nonlinearities in a system. There has been a debate within the community. So you can add nonlinearities in a system to represent the asymmetry between El Niño and La Niña. But then these nonlinearities that you add in a system, you can interpret them either as coming from oceanic processes or coming from atmospheric processes. My own view is that atmospheric process dominates the nonlinearity, basically the asymmetry in the convection. I mean, the fact that the convection depends on background SST as a threshold. There is a threshold for convection. And actually, recently, with a student of mine, we did a study trying to test the effect of oceanic nonlinearities. And the surprising thing, so there are many oceanic mechanisms that could involve nonlinearities, vertical processes, so mixing, the shape of the thermocline, etc. And another class of process are tropical instability waves, which are bringing a lot of heat to the equatorial band. In the estimates that we did, that's in an ocean model, the effect of vertical nonlinearities in the ocean and horizontal nonlinearities in the ocean seem to cancel out almost exactly. So if this is correct, I mean, I don't know if this is correct, and this is only one study with one model, then it probably means that in the end, there are a lot of nonlinear processes in the ocean, but for some reason they cancel out. And what we need to worry about is the atmosphere. But we don't know. So, and you may be right that there may be some complex vertical process which also contribute to nonlinearity. So I don't think this is a solved question, and probably more research is needed. But I would say that what we show is that to first order, by taking a simple linear relation, we get a reasonable behavior. We can already explain many aspects of the system. So maybe to fine tune a little bit what we can say about higher orders, we need to understand. And anyway, it's always good to understand better the physics of the Eastern Pacific. I mean, this is an essential place for El Niño.
Thanks. I'm going to read that study, but I want to give the room to someone else's questions because we do have a question now in the chat. Hayemi Kim says, sorry if I butchered your name there. Thanks for the very interesting talk. Regarding the ENSO predictability, how much room do you think is left to reach the theoretical limit? Say, is 18 months an upper limit?
Yeah, so let me again come back to one slide which can illustrate that. Okay, so this is one slide. So we are currently working with people who are involved in the Recharge Oscillator review. We are working on we will soon release a community version of the Recharge Oscillator available for everybody to use in Python and MATLAB. And this is one figure from the paper that we are putting together on this. And it shows actually the skill score that you can achieve with the Recharge Oscillator. So it's the pink curve. And actually the pink shading is showing the range of skill that you expect from a theoretical, from a perfect model. And you see that if you use the extended Recharge Oscillator, so both internal dynamics to the Pacific and influence of a region, you actually go over the skill that you have purely from the Recharge Oscillator from internal Pacific dynamics. So I would say probably the scope for improvement is not that great. We see that already with the Recharge Oscillator plus adding over influence of our basin, we already beat artificial intelligence at long lags, and we have something which is slightly better for NMME. So I would say this is already really high skill at one month link, but it's difficult to know actually.
Thank you. And then the question asker thanks you as well. So thank you very much. Okay, well, if there's no more questions or hands raised, then I'm going to let Jérôme go because you've already given us more of your time. Thank you so much again for starting us. I hope everyone recommends the recording to their students, postdocs, people who want to get into ENSO. I know I will. I think it's a great way to start understanding this very complex system. So thank you very much again, Jérôme. Thanks, Cliver and the Pacific Regional Panel for helping us set up this webinar series. And thanks everyone for coming and staying with us for longer than we initially said you would.
Yeah, thank you very much. And I'm looking forward to seeing more talks in this very nice webinar series.
Yes.
Have a good day.
Bye.